So relaxation time, noted as T1 and T2, are the time it takes for protons to return to their normal energy state. And there's two different times that can be measured. T1 is the time it takes the protons to relax and transfer their energy. So protons flip over, then flip back, and then their energy is transferred into molecules surrounding them. If the surrounding molecules have a natural frequency close to the Lamont frequency, the energy more rapidly goes out of the protons into the tissue surrounding them. Whereas the T1 times are better used for fats, carbohydrates, and solids. T2 times, we're measuring the time for protons to go out of phase with one another, so that the energy is spread to other protons. The T2 is short for solids and larger molecules such as fats, carbohydrates. And if the pulse rate is slow, watery tissues will have time to release and relax before the next pulse is sent in by the machine, so they'll appear bright. So T2 times are good for looking at watery molecules and things with a lot of water in them. Sometimes we need to use a contrast medium. This is something just to make the difference between T1 and T2 a greater contrast, make it appear better on the displays. So MRI signals rely on the signals from the hydrogen nuclei in fats and water, and that's the T1 and T2 times. Gadolinium is something that can be used as a contrast agent, which shortens the T1 time of protons around it, and makes those tissues that have a short T1 time appear brighter. And it's gotten rid of out of the kidneys very quickly, and it has a short half-life, so it's not affecting the body. Okay, so once again, those tissues with a long T2 time tend to be water. Those with a short T1 time tend to be fats, solids, so on. So just to stress, the T1 and T2 times of different tissues help us to contrast or detect what type of tissue is showing up in the MRI. Those with a long T2 time tend to be watery tissues. Those with a short T1 time tend to be solids, liquids, and fats.